Hello, my name is Vicky Stone. I am at Heriot-Watt University in Edinburgh in the UK, and I'm the coordinator of the Gracious project, which is funded by the European Commission. So this project has made a framework to support grouping of different nano forms together. You may be aware of the term nanomaterial. So nanomaterial is something like a titanium dioxide particle, and then a nanoform would be different versions of the nanomaterial. So it could be different sizes, different shapes, different surface coatings of that titanium dioxide. So this framework is about grouping different nanoforms together so you can infer information from one nanoform to fill data gaps for the other. And we'll look at hypotheses that support grouping and ways of collecting data via something called an IATA to support that hypothesis. So conventional risk assessment requires you to consider risks on a case-by-case basis, but this is really expensive. It takes a lot of money, it takes a lot of time, and it uses potentially a large number of animals. And so really we need to streamline this process. So grouping provides a way of intelligently streamlining your information for risk assessment purposes. Now, this is possible according to the European regulation. So the European regulation that regulates chemicals, substances and nanomaterials is REACH. And within REACH, it says that you can group together similar substances based on their physicochemical toxicology and ecotoxicology properties. So you need to be able to assess similarities. So it's fairly easy to do a qualitative similarity assessment based on expert judgment. But within the Gracious framework, we've also generated some methods for a quantitative similarity assessment, which Nina will describe to you later in this session. So the Gracious project started in 2018 and it's due to finish later this year. We have 23 partners from across Europe and two of those are in the US. And as I said, I've already told you, this is about making a framework to support the grouping of different nanoforms. And one of those applications that you can then use the grouping framework for is to read across data from data-rich substances to those that are lacking data in order to fill their data gaps. So the Gracious framework has already been published. It was published in Nano Today in 2020, and this is a simple version of the Gracious framework. So you would start the framework either with a single nanoform that you're lacking data on to help you do a risk assessment. And so you're looking for a group that you could insert your single nanoform into that contains the data that you need. Or it could be that you have a provisional group of nanoforms, some of which have data and some don't. Then you need to go through a basic information step where you collect enough information to trigger a specific grouping hypothesis. So the European Chemicals Agency requires you to generate a hypothesis that explains why, in a scientifically valid way, the reasons that you want to group your nanomaterials together. And then within this detailed step, once you've generated your hypothesis, we then have these structures available that allow you to assess that hypothesis and gather the available information or generate new information needed. And any generation of new data would use a tiered testing strategy, where tier 1 would be simple methods, tier 3 would be more complex models, in order to generate the data that you need to assess whether your hypothesis is valid or not. If it's valid, then you can go ahead with your grouping decision. If it's not, you might either choose to refine your hypothesis and reassess it, or you may decide that you want to just assess the risk on a case-by-case basis. Applications for the grouping framework include development of dossiers for the regulator. So if you want to sell chemicals in the European Union, once they reach a certain tonnage value on the market, then you have to submit safety dossiers to the European Chemicals Agency. So it can be used to support this. It could be used in the early innovation stages of either nano forms or nano-enabled products. So if you incorporate safety into the design of such a substance, this is known as safe by design or safer by design, as indicated SBD. You also could use the framework to help you refine a testing strategy for nanomaterials, and also you could use it to help inform any precautionary measures that you want to do in terms of controlling risk for workers or for the consumer or for the environment. So this is a more complicated version of the Gracious framework. So it's the same framework as in the previous diagram, but just with more detail. So you'll still enter with a single nanoform or a provisional group that are lacking some data. And then the basic information includes physical and chemical characteristics. These can be estimated values or they could be known values, so measured. And then release and exposure information. This is important to allow you to understand routes of exposure for humans and relevant environmental compartments. Again, these could be estimated values or known measured values. And then also we want you to identify the purpose of grouping, because this allows us to understand the level of detail that you need in the outputs from the framework. This information is sufficient for you to generate a grouping hypothesis. We've already generated a number of predefined hypotheses using data from the peer-reviewed literature and from databases. I've just shown some abbreviations for a few of these hypotheses here, and we expect that this database of hypotheses will be expanded with time. If any of the hypotheses we provide are not suitable for the user, we can also generate a user-defined hypothesis using a hypothesis template. Once the user has their hypothesis, they then need to test it, and it's tested using a testing strategy known as an IATA. IATA stands for Integrated Approaches to Testing and Assessment, and I'll describe what that means in a moment. This IATA is tailored to the specific hypothesis so that you only generate the information that's really needed. When you conduct the IATA or use the IATA, it will generate information which is collated together using a data matrix, and this data matrix is required by the European Chemicals Agency for regulatory purposes. The purpose defines the level of detail and certainty within the data matrix of the information that you have, and this impacts on the number of tiers that you might include within that data matrix for any of the specific endpoints measured. Once you have your data matrix, you can then assess the similarity of your nanoform members within the group, and then either decide to accept your grouping hypothesis, to refine your hypothesis, or to assess risk on a case-by-case basis. So one of the applications that you can use grouping or the group for is to lead to read across, and Agnes will talk more about read across in her presentation later. But briefly, what this means is that within your group, so you've identified your group, there will be some nanoforms that have data available to support risk assessment, and there will be some nanoforms which lack data, and these are known as your target nanoforms. So the idea is that you use your grouping hypothesis to generate a read across hypothesis. You use your data matrix to decide whether to accept or reject your read across hypothesis, so that you then have a justified read across decision from your source material to your target material. I've also mentioned that you can use the framework in the early innovation stages. This is called the stage gate process, this diagram here. It's the gates or the stages that people might go through from the initial concept or discovery of an idea for a new nanoform or a nano-enabled product through to its launch onto the market. And so there are a number of steps or stages that the individual would go through, and between each stage are gates where you would make a decision whether to continue or to stop the discovery process or the innovation process. And we've mapped the framework onto this stage gate process. So the basic information step maps onto steps 1 from scoping through to stage 4, testing and validation, while the detailed step maps onto stages 3 from development through to stage 5, the launch of the product, when you would need to generate data suitable for a regulator. I'm now going to talk about the grouping hypotheses. So this is the hypothesis template that I described earlier on. So it helps you to generate a hypothesis that includes all of the information needed in a way that's consistent from one hypothesis to another. So it allows you to indicate the purpose of grouping, but also the context. So the context means, is it for an environmental application? Is it relevant to a consumer, or is it an occupational setting? You then need to consider the life cycle stages that are most relevant to your risk assessment. So is it during production, use, or um, release of your nanoform into recycling or disposal? And then you need to consider these three questions: what they are, which covers physical and chemical characteristics; where they go, so where they go in the environment and where they go in the body; and then what they do, so their hazards. So we actually have 40 predefined hypotheses within the GRACIOUS framework, 17 for human hazard and 23 for the environment. So here are a few examples of hypotheses. The first one is for human health, and this one's relevant to quickly dissolving nanoforms that enter the body via inhalation, and it stipulates that both nanoforms and the constituent ions or molecules may contribute to the toxicity associated with that exposure, but there should be no concern for accumulation. The next hypothesis is for the environment, and it covers nanoforms with a chemical coating, and that chemical coating is not stable, so it's lost. And in the soil compartment, you would therefore need to consider both the fate and toxicity of this nanoform, and you could look at non-coated nanoforms in order to group them together. So we haven't just covered inhalation for humans, we've also looked at ingestion and dermal routes of exposure, and for the environment, we've also included the aquatic environment, sediment, and the air. This is an integrated approach to testing and assessment, or an IATA. This is a generic one. It covers exposure, phys-chem characteristics, the compartments in the environment or the tissues exposed, and the mechanism of hazard. So these are questions in a decision tree that allow you to make yes or no decisions. If you make yes decisions throughout, then you confirm your group. If you make no decision at any point, then you deviate from your hypothesis and your group's not accepted. These questions we've called decision nodes, and the questions in here are tailored to your specific hypothesis, so you have a tailored IATA. In order to make a decision, you need methods to interrogate that decision. So we provide tiered testing strategies that include a range of standard operating procedures that allow you to assess and generate the data you need to answer these questions. To answer yes or no, sometimes you need a threshold value above or below which you can say yes or no. These threshold values are really difficult to justify scientifically, and so the alternative method that we've provided are quantitative methods to assess the similarity of your nanoforms within your group. Once you've gone through the IATA and generated the information needed, then this will help you to generate a data matrix to support your hypothesis and your similarity assessment. The good thing about IATAs is it doesn't just focus on the generation of new data. It allows you to combine existing data from the literature and databases, as well as using computational approaches in order to populate your data matrix, shown here, with information so you can decide whether your nanoforms are similar to each other or not. This is one of our super IATAs that covers the oral route of exposure. So it's an oral IATA, and it has a series of, as I've said, decision nodes with yes, no answers. These are some answers or some information for the user to guide you through the decision node. So this IATA focuses on dissolution as being a key physical and chemical characteristic that determines whether you're exposed to just the dissolved material or whether you're exposed to a mixture of the nanoform and dissolved material. So at this end here we have very quick dissolution rates as indicated by a half-life of very short duration, through to more biopersistent low solubility materials with a very high half-life. So first of all, we assess dissolution in the gastrointestinal fluids, and this allows us to decide whether our nanoform is instantaneously dissolving, quickly dissolving, gradual, or very slowly dissolving. For the instantaneous dissolving nanoforms, then we just assess their toxicity based on their composition and their constituent ions or molecules. For those that are dissolving quickly, gradually, or very slowly, we need to consider their dissolution inside the cell in a compartment known as the lysosome, where there is a pH of 4.5. And again, we've used half-lives to indicate their rate of dissolution so that we can decide whether they are not biopersistent, or highly biopersistent. Once we have that information, we then assess the toxicity of the nanoforms and the constituent ions, or just the nanoforms on their own, in order to decide whether they're sufficiently similar to each other to be grouped. So just to summarize, this IATA includes dissolution in the gastrointestinal tract fluid, dissolution in cells, and then an assessment of hazard. To consider hazard, we have a range of different endpoints which need to be considered, such as surface reactivity, cytotoxicity, ability to induce inflammation, and also genotoxicity. Behind each of these decision nodes is a tiered testing strategy with 3 different tiers. Tier 1 being simple methods, such as in silico, in chemico, or in vitro methods. So in silico is computational modeling, and chemical is just chemical testing, and the simple in vitro models would just be a monoculture of one cell type. Tier 2 would be more complex models such as 3-dimensional multi-lineage pathophysiologically relevant cell cultures, and Tier 3 might be animal models. At each tier, we encourage the user to review the existing data available to them rather than going straight to testing, and only do testing to fill data gaps. As you move along the tiers, the level of certainty of the data that you generate probably should increase. And this is important when we think about the purposes of doing grouping. So tier 1 methods are often sufficient for safe by design, but if there's too much uncertainty, you can move to tier 2 methods. For regulatory purposes, tier 1 may be sufficient, but it's likely that in some situations you may need to move to tier 2 or even a tier 3 method. So as I've said, there are a range of SOPs or standard operating procedures available to us. At the tier 1 level, there are some regulatory accepted methods available provided by organizations such as the OECD and ISO. Unfortunately, at the tier 2 method, there are very few or no regulatory accepted methods available. For the skin, there are a few, but for other organs, there are none really. Projects such as Patrols have started to publish such models, which will be useful in future as evidence increases to understand more the certainty or uncertainty of the data generated by such models. And then tier 3, there are a large number of regulatory accepted methods available. So this is what a tiered testing strategy looks like. It's quite complicated, so don't panic. So along the top here, we have the different decision nodes, and then below we have the tier 1, tier 2, and tier 3 methods indicated, with reviewing the existing data indicated for each tier. And then within each box for each decision node, we've indicated the most relevant standard operating procedures that are currently available for people to use. So just to recap the GRACIOS framework, so you can enter with a single nanoform or a provisional group. You collect your basic information in terms of phys-chem characteristics, release and exposure, and identify the purpose. You generate your grouping hypothesis. You test your hypothesis using the IATAs, to populate a data matrix, and the level of certainty you need is dependent upon your purpose. You can then accept your grouping decision, refine your grouping hypothesis, or assess on a case-by-case basis. So once you've done your grouping, you can use this to fill data gaps for hazard. You can help to inform exposure information or risk information. It can feed into the design of risk management measures, and it can help to inform safer design of new nanoforms in the future. So thank you for listening to this presentation, and we'll discuss some questions in the discussion session. Thank you.